All right, we're going to go ahead and get started. Happy Thursday, everyone. Thank you so much for taking time out of your day to join AI Futures and at Naval Surface Warfare Center, Philadelphia Division. So my name is Jessie Stafford. I am the Brand and Strategic Relationship Coordinator here at AI Futures, where we put on events such as what you're going to have today with Dr. Stephen Mastro. So before we hand over the mic to him, I just wanted to give a little bit of an overview of our program and what may be of interest to you here in the future. So we are a workforce development program that is funded by the Department of Defense to help spread awareness with internships and full-time positions within the DoD as a civilian. So we do that through free student services. So you have the opportunity, if this is of interest to you, to set up some time for an informational session to get your resume reviewed, get some guidance on setting up your profile in places like USA Jobs, and really get to talk about what kind of opportunities are out there that may be of interest to you. So typically we do work with quote unquote STEM students, but we also work with project management, obviously, business acquisition, HR, and accounting. So there are an assortment of job opportunities all across the country, depending on where you're located. And obviously, NSWC Philadelphia Division is one of those opportunities that can be talked about. So outside of our technical talks, we do offer additional opportunities where we sponsor events like your local hackathon. So if you have universities that have those put on, we often like to participate there. And then as well as doing different events like AI ground vehicle challenges, where you get the opportunity to essentially bring a robot to life and guide it through a maze. So a lot of cool things to interact with AI features. So keep an eye out on Handshake for any type of future events that may come across your path outside of the normal technical talks that we do sponsor. Okay, so I'm going to go ahead and introduce our guest speaker today. He's why you're here. So we have Dr. Steve Mastro. He is the Deputy CTO at Naval Surface Warfare Center, Philadelphia Division. That's a tongue twister. He is going to be giving a talk on systems engineering and project management. So we're really excited to be able to host him today. We've had a lot of great talks in the past with Philadelphia Division, with Tristan Wolf, who is also on this call. So we always are thankful for those opportunities. So without further ado, I'm going to go ahead and stop my screen sharing and pass the proverbial mic over to Dr. Mastro.
Okay, thank you. Let me, hold on a second. See if I can, here we go. I'm sharing. Give me a second here. Hello, everyone. Let me get into the right mode here. It's up to do. Okay, here we are. Hi, everybody. I'm Steve Mastro. I'm the Deputy Chief Technology Officer at Naval Surface Warfare Center, Philadelphia Division. What that title means is that I work with various aspects of technology with all of our engineers. We have about 3,000 people, 2/3 of which are technical, and I get to work with research stuff and get to work with also in-service engineering, which is repair and maintenance of systems that are already on the ship. And put very simply, what we do in Philadelphia is shipboard machinery systems and electrical systems. I was where you are 30 years ago. We were not using computers on desks. Engineering was a lot more old-fashioned 30 years ago. But what I wanted to cover with this, what systems engineering is and project management, is how we do what we do more than what we do when we're doing our engineering. So where I want you to think about is, you all may understand that in engineering, in any STEM field, that there are individual things we learn and things that we do, technical things, right? It could be solving equations, it could be writing things, designing things, observing things, testing them. Okay, that's fine. And that we know that, and we know, which I'll show in a slide coming up, that somehow we needed something and engineering happened, and then we got products or solutions or things to help us do that. Okay. But how did we get from what it is I need, right? I need to communicate. I need to get from point A to point B. I need gasoline, or I need plastic, or I need polymer fiber, or paint, or whatever. Okay. Or I need a place to go where I can sit in a building and do what it is I need to do. How do we move from what it is we need, okay, to a technology-based solution? There's many ways to define our profession, but if you were going to define most STEM areas of business, just like doctors heal and lawyers represent and accountants take care of math and business, right? This is what engineers do. Very simply put, we go from a need, a requirement. We need something, and what we need is endless, right? Because we need new things and we need the things we have already to be better, right? You can look down that list on the left, and at the highest level, meaning the most basic level we could express it, these are the things we need, right? If you look at all of those things, and if I had you come up with a list, you could come up with a list of 100 things that we need. This applies to the Navy, but it applies for absolutely everything. Okay, so in blue is what we're doing, right, with the Navy. So we have all of these things we need, and then we do something, right, called engineering. And at the end, we have things that fulfill those requirements. Okay. And this is really a condition of life. It's the way our brains are set up. I always joke that children are system thinkers, right? There's a requirement, and I need to get to the end. I need to get to that thing that will fulfill my requirement. Okay. And so just giving you examples, that's it. And that is what engineering is. That is what engineering does, is at the very most basic principle, takes things that we need that are identified at different levels of sophistication and provides some kind of solution that is somewhat technology based. That doesn't have to be hardware or software. It often is, but it could be a process. It could be a scientific principle that's used to get what we need. Okay. And that is what engineering is. So when I talk about that in this context, this is the kind of shift in this overarching topic called systems engineering, which, by the way, there's a few undergraduate engineering majors with this, lots of graduate programs in system engineering, and you can look that up. Do a web search on systems engineering, and you'll see an awful lot of things. But systems engineering is less about what we are doing our analysis, doing our testing, doing our design, writing code, using AI, doing whatever it is we do. It's less about the what and about the how. And sometimes when we stampede to what and don't think about how, we get into trouble. But if we think about it, the how is, well, how did I go from that need to that solution? In what order? Where do we start? Okay. And by the way, not giving you all the answers. If you get anything from this talk, think about this topic to ask great questions. Wherever you work, find out where you are in systems engineering and ask others how they're doing things that make this work flow along. Also, when you do a job interview, right, think about these topics I'm going to talk about and ask the employer, how do you come up with your requirements? How do you work together to make things happen? But that's what systems engineering is really about, is about the how. Okay, so in time, we can think about a technical flow of activities, meaning how do I go from, I need something to having that final answer? What is the flow of activities? Where do we start? How do we go through that in time? And also about the control and execution of activities. That's a lot of words to just mean how of the how. Like, I understand that we have to do these steps, but now how do I use technology, people, money, a business, a factory floor? How do we actually make that happen? And that's where systems engineering and project management comes into play. What we think about is that systems engineering is more geared towards the technical flow of activities, how we're going to do things in some kind of orderly fashion to start with what it is we need, develop different possible solutions, pick one, design it, build it, test it, and then eventually have it come out in a way that's profitable for a company, in a way that's fast enough that it's helpful, that's fast enough that your competitors, you're in there with your competitors providing updates and things like that. Okay. And then the control and execution of those activities, that's where program and project management comes in. That means managing your time. Okay. Not just yourself. When I talk program management and project management, we're talking about companies that can have anywhere from 20 employees to 20,000 employees. How do we manage all of those people and where they work? How do we give them IT and everything else they need to get their work done? How do we give them the tools so they could maximize their PowerPoint slide properly, which I'm not able to do today. Okay, but that's basically how those two subjects feed in. That's why I call project management the how of the how. We'll see what that means in a second. So systems engineering is something I was doing for 15 years, not knowing it had a name. Okay. And formally as a topic, it came up in the mid 20th century. And the reason it came up very basically is that engineering and the development of technology was very much coming up with ideas, building them, testing them, a lot of trial and error, physical trial and error to see if things would work or not. And if it didn't, you would go back to the drawing board and you would update it and make it work. Okay. The problem is, as we got into the the first third and the middle of the 20th century, our systems started to become so sophisticated and so expensive, and there was such a rush, especially during wartime, to get things done fast, that building things to figure out if they would work and then fix it later was too expensive, and it took too long, and it was too wasteful. So the idea was to come up with a process, if you will, an approach to do engineering that would eliminate that kind of waste. Okay. So what's interesting here is these principles of systems engineering are not like first principles that you get from Isaac Newton or from some physics equations. A lot of these principles of systems engineering came from observing what worked and what did not work. What companies that were successful, how did they do their engineering? And the ones that went out of business, how did they do their engineering? And coming up with these principles of systems engineering that help this flow, almost like the directions to put furniture together or something like that in an elaborate way. How do we know how to do our engineering, especially when you're talking about, this gets very difficult too, when we're talking about big companies like the car companies or Apple making your cell phone or something like that. Okay. And that's when it all started and became more of a formalized process. Okay. So I'm not going to read this to you, but this is a definition of systems engineering. You look online, you'll find 100 definitions of systems engineering. As I always joke, they're all correct. They just look at it a different way. Okay. And I already mentioned that. So I'm skipping right now. Systems engineering is an entire graduate degree. In some cases, in some limited cases, an undergraduate degree. You could spend a whole course talking about this. I'm just talking to you about the process in general. But in order to make these things happen, there's a lot of sophisticated tools, processes, people, and infrastructure that allow companies to do systems engineering, along with many big companies and the Defense Department have manuals on how you should do things in order to help the engineering be better. Okay, so this process that I'm talking about, again, I show two different ways you can look at it, but this is a good basic way to look at what is the systems engineering process. Okay, you'll see this a lot if you do a web search, the so-called V diagram. And of course, there's many complicated ways to present this that I don't think are very useful. It's really very simple when you look at the very basics of this process. Okay. The idea is to start with an accurate idea of what it is you need, then coming up with concepts on what could fulfill that need. And very important at that stage, not coming up with just one answer, which is really what you're all taught. And there's a reason for that. But as undergraduate engineers or undergraduate STEM students, you are very often told to get the answer to a problem. There's one answer to a problem. Just like when you were children and when you get out into the world as engineers, it's important to remember that there are a number of solutions to a possible problem or need. And then, so it's a good idea to come up with multiple solutions and then somehow try to find out which one of those solutions is the best one. Okay. And that's concept development. Once you come up with a general concept of how you want to address that need or requirement, you then start talking about the specific technical requirements. How high, how fast, things like that. If our solution is a building, how tall, how big, location, things like that. Okay, that's requirements. Then we just start the design process by looking at a system architecture, not a detailed design of exactly what the solution is, but looking at functions of what the system has to do. And then once we know the functions, we can get to an actual detailed design of something, a car, a cell phone, a gaming system, whatever it is, electric bike, whatever. Okay. We design and then build that system. And then we do tests on the physical system, prototypes. These days, and I mention here, that's what this thing in the middle is, these steps should all be, information should be flowing between all these steps. And the reason I mention that now is because after we design something and build it, we'll physically test it. But today, what you all are learning in school with modeling and simulation, you could start that testing back here as you're coming up with designs and help you choose which design by doing tests virtually. And that's why I mentioned that here. Okay. But then we figure out that the product works and it's okay. And then we build it and then produce it. Okay. For everyone to use. If this system works right, then all of these steps will communicate with each other. What do I mean by that? Well, when we did testing on something here in the test and evaluation box, when we saw things that failed, that didn't work right, we're going to put that information all the way back into concept development, right? We're going to say that, well, we tried these other ways of doing things and we found out from testing it didn't work. So when we come up with our requirements, we're going to avoid that. Also, if we looked at design and test and evaluation and building something and it's selling well, we will use what's working well and put that in as a requirement, saying our customers really like this, or this made our product reliable, it didn't fail, everything else. Okay. So very simply put, that is what, and you'll see it listed in a slightly different way later, but that is what the systems engineering process is. It is a flow of activities, of technical activities. So the what of engineering, you applying, using MATLAB, doing design, testing something to see if it works, listening to customers, in our case, listening to the fleet on something that's breaking, that's not reliable, all that stuff, that happens within each of these steps. And the process shows you the flow of what happens with all of those stages. Okay, so that was very, very quick what systems engineering is. So, okay, that's great. I just explained that we're going to do these things. Okay, and I always joke, go into a company, look at people in a meeting, on a Teams meeting like this, or a Zoom meeting, or go into a company and look at everyone that's working there. And, well, how do the people I work with actually make this happen? How does this actually happen? How is it organized? How does it get paid for? Everywhere in those activities I just told you about are human beings doing engineering work. They have to get paid. They need health insurance. They need a place to work. They need equipment, and that all requires money. Well, who takes care of that? And as you probably already know, a company of 3,000 people is not one boss with 2,999 employees. How do we organize ourselves? How do we communicate with each other? That that stuff, the connective tissue, as we sometimes call it, how we run the store, if you will, just like running a business, running a store, running a baseball team, uh, running an amateur theater troupe. There needs to be some sort of organization and business processes, and that's where project management comes in. And this is a challenge in medicine because we're dealing with doctors and biology and all of that other stuff. And program management and engineering, we're dealing with the movement of technology. So it helps when we deal with program management to have a mind for technology and how that could be made to work and flow through those different steps. So not reading to you, but you can see that paragraph basically um, describes what program and project management is. So the key features of this are the things I've listed on the left. Okay. Execution, meaning how is money flowing? How are things being accomplished in time? We keep in mind that it's not one single flow of work making all this happen. There are thousands of people working on different things that have to arrive at a certain point to then connect up, have a product to then move on to the next step. Example, you've got an antenna in your cell phone, and there's going to be some antenna design, improvement in the antenna design, but they need to know how capable the microchip that is specifically designed for the antenna is going to come out before they finish optimizing the antenna, right? Things have to happen in some certain order. And so timing of how things are getting done, resources means money and people's time. Um, and that relates also to infrastructure, laboratories, building, equipment, computers, filing cabinets, post-its. It sounds silly, but all of these things have to be accounted for. Okay. And also, probably one of the most important things project management covers is the monitoring and the control of the progress of everything being done. So we can have these timelines of how work should get done, but how often are we going to check in? How often am I going to ask people doing that technical work to let me know what progress they've made? And in what format? Are we meeting? Are you sending me a report? Is it going to be PowerPoint slides? Is it going to be a Word document? What is it that you're going to share with me in order for me to be able to say you're behind schedule and need to speed up, and I then have to get you more help if that will help, or more money if that will help, etc. So this gets complicated very fast. And so when you talk about project management, those are the heavy hitters, the most important things. But you'll see all these little things in that little donut, which if my bifocals work better, would be easier to see. But we talk about cost management, budgeting. I always make this joke that we think of money as being something for people who pursue business and accounting and finance to take care of. Money is an engineering parameter. What you choose to do, the materials you choose to do it, your design, all has financial implications. Okay. You might decide for the Navy that you are working on deciding on which of three different completely different engine technologies for a ship might be. So not only are there technical aspects of that, but because they use different kinds of fuel and they have different kinds of efficiency, money is one of your parameters. So cost of getting the project done, but also costs related to the technology also come into play. And that's part of project management. Okay. Quality, communication. I mention everything I've just mentioned up till now as if all human beings can just go like this and know what everybody else is thinking. How we communicate data, whether it's in written form, verbal form, meetings, however, presentations, however we're communicating in our profession, communication is very, very important. The same way it's very important for physicians to be very precise when they are talking about treatment and medication and everything else. So too, even as a junior person, as an intern, let alone a young engineer or STEM professional, to ask questions. And if you see something that doesn't seem right, to communicate that you see that something may be right. And that is one of the biggest parts of project management as well. Procurement management, what does that mean? It means that no matter where you work, you are buying things from someone. You're probably not digging base metals out of the ground and making everything you need, and making your own plastics and everything. You're buying material, goods, services, IT equipment, lab infrastructure. You are buying things, and that has a technical component too. And that's part of project management, is aligning all of that buying of equipment and resources in order to get your job done. Okay. Another big one, lower left there, risk management. When someone tells you, I am going to have that new antenna chip designed by next July, okay, is that a 100% guarantee, or is there risk? How likely is the risk that something could delay you? And if that risk does happen, how bad is it for our overall progress? Risk evaluation is something else program managers do. Okay. And lastly, but certainly not least, project management, human resources aspect, which means we are human beings. We are not robots. So identifying people's individual skills, having them working on the right thing that they have competency in, interest in, can get done well. People working together, switching your team up to optimize how they get things done, and all of that. So that's all involved with project management. So as you can see, what we're going to do in systems engineering, the fuel for that is this is project management and making sure these things are all done. And in the end, this is important because it optimizes our product, meaning what it is we're designing comes out better, or working on or repairing is done better and is done as affordably as possible. In the Navy, we're in the public sector. We use tax money, so we're supposed to have a duty to try not to waste money and spend money smartly. If you work in the private sector for any private company, they're in business because they're making a profit, and that profit gets optimized, okay, by you controlling the costs, which isn't to say you don't spend money where you need to, but it means you don't waste money, and that's very important in the private sector. Okay, so on the left is a sort of list view instead of that V diagram of how we go through the systems process. And on the right is the graph I just showed you for project management. The key and the thing that successful companies do very well is matching these two things. So they're going down the list of technical things they need to do here on the left, right? These are fancy words that, but you know from before what it means. Coming up with our basic need or requirement, how might we approach that? And then once we know how we're doing the approach, what are the actual numbers for the requirements? How big, how fast, how heavy, okay? What functions does the system have to do? And then designing it, okay? Testing it, making it. This is not trivial. That's important too. And then using it and possibly retiring the system in an ecologically responsible way, okay? So successful companies match doing that along with these things I just mentioned, okay? Because doing this well helps you get through these steps of the systems process efficiently. And so there's overlap, right? Those things are intertwined with the steps on the left, right? So I'm doing, let's say, design, and I'm trying to do things like project risk, project cost based on what I'm designing, right? Let me give you a really simple, it's a silly, funny example, but it makes the point here, is that I am coming up with designs for snow shovels. And two of the designs, one of them uses aluminum, which has the risks of bending and not staying, not staying the way it should be for a very long time. But I have another shovel that's made out of titanium, right? And that works really well. But the risk there is what? Is that my snow shovel would cost $1,500 if I did that, right? So cost and risk of performance. Another example that I always use as we match these two things. What if I said to you that it would be very easy from a technical standpoint to eliminate 99.9% of all traffic fatalities? We could absolutely design a car that would reduce traffic fatalities 99.9%, right? So follow me technically. It would be a car with a roll cage, with a very strong body, like a race car, okay? It would have a 5-point seat belt that you couldn't drive without. We would make the driver of the car wear a crash helmet, okay? And the car would have an automatic suppression system, right? We would, by designing a car such like that, with sophisticated materials, bumper materials around a roll cage, 5-point, wearing a helmet, fire suppression, we would eliminate almost all traffic fatalities. So from purely this systems view and from a technical view, we're good, right? But what's the obvious problem? The car would cost $750,000, right? It's not affordable. So a solution that doesn't come in as affordable doesn't really do us any good. So I'm giving you these extreme examples. Obviously, the real world is somewhere in between. Last example, because we're almost done with the slides. iPhone 15, I think, latest one. Apple did not want to buy Qualcomm chips for their antenna. I keep pointing to the camera, but as an antenna, cell phone antennas have a dedicated microchip to run the antenna, and they bought them from Qualcomm, for which they've gotten in lawsuits with Qualcomm and all this other business. Okay, they were dedicated to having their own Apple designed chip for the antenna. This was planned 2 or 3 years ahead of time before this phone came out. Apple's a very good company. They do excellent engineering. They couldn't get the chip done in time. They made progress towards designing their own chip, didn't make it in time. And so all the iPhone 15s have Qualcomm chips because they had no choice. So along the way, as they were doing that, they put billions of dollars into this, and they did that, and they will succeed at some point. But my point is there was risk involved because it was a difficult technical challenge. You may not think about this, but that chip is doing some pretty sophisticated things, which is why you can go around the world. You can go to Europe, you can go to Asia, you can go to South America, and your phone just works. And part of that, even with the different systems and different infrastructure and different companies, that works, and the chip works very well, and it's something Qualcomm specializes in. So so that's a little more of a subtle example of them going through all this project management stuff and the systems engineering stuff to try to make something happen. And that's why that's a big part of what they do. Okay, so I talked about a lot of these as far as I'm concerned, right? These are the top hits when we look at doing these things together, making that systems process work. along in the context of project management are these things on the left. Communication between all of the teams. Who is doing what? This is something you do yourself when you and a bunch of friends are going out to dinner. Who's going to do what? Who's picking where we go? Right? You sort of do this just naturally when in your everyday life, or working in a small business or something. This gets very difficult with high tech and with large companies, right? Requirements transparency means when I'm all the way down here designing things and building things, I want to make sure I didn't leave any of these requirements out. Did we design something and build it and we kind of forgot? Remember, in a sophisticated system for something like even that cell phone, there are thousands of requirements, technical requirements for that. Did we leave anything out? Right? That's what requirements transparency means. Planning, scope, how big or narrow each person on the team is doing something. Okay. And these other things which I've talked about. Also, interfacing with your end customer, making sure what you're designing is still matches what it is the customer wants. Okay. Let's move on. I want to leave time for questions. Okay, so you could just read this. I'm not going to read it to you, but these are topics that sort of cut across everything you might be thinking about working in a STEM field. It actually applies to all STEM fields and even other STEM fields. If you look at the logic behind these processes that I'm talking about, and over the years, we've noticed that the companies that do this well succeed. And wherever you see companies that are not doing well or technologies that have failed, if you all are, you might in the news read about different engineering failures. Boeing has had some, with all apologies to my friends and colleagues that work for Boeing. The BP oil rig in the Gulf of Mexico, pedestrian footbridge failure, Florida International University. When you look at those engineering failures, or in failures of products that didn't sell well or didn't do well in the market, you can always look back at these factors, systems engineering and project management, and see what went wrong. But what I hope just from this basic talk you get is this is really about this is really about asking good questions and helping you and your colleagues, your fellow students, do your best work by making sure it's following good principles. And that's why, back to the beginning, I say this is more about how we do engineering than the what of the engineering. Oh my goodness. Oh, you're not seeing that. I'm sorry. I'm getting pop-ups all over my. Okay, so that's enough of the. That's all I have for the PowerPoint. How do I? I'm going to try to stop sharing. Let me see. Stop sharing. I think I've stopped sharing. Have I stopped?
Yep, you're all good.
Okay.
Okay.
That got me very flustered. Yeah. So are there any questions?
Yeah, we do have some queued up here. I can read aloud for you. So the first one is from Vishwa, who they're citing out the V diagram that you presented earlier with the flow of system engineering processes. And it seems very similar to the process that you undergo for the research that many of us have used in our undergraduate research labs, as an example, the scientific method. So how is systems engineering different from this sort of research work besides different specific use cases, or is it really different at all?
It's not different at all. It's not different at all. This is, as I said, it's to a different degree. This is expanded, and systems engineering is the scientific method tailored for engineering and our field. But it is no different than the scientific method. It's a logical progression of the way that you would approach something, right? So that scientific method with coming up with a question and then what are the different, and then setting up an experiment, verifying your theory, it's the same thing. It's just tailored more towards engineering. Now, keep in mind when I talk about a formal systems engineering guide that you might have at a big company, it goes into much more detail about exactly how you should approach these different things. So where you would have the scientific method for your research work at school, um, just imagine that expanded more, where the school would have given you a guide of, okay, not only are you going to do this, but this is how you're going to write it. This is what style you're going to write it. And when you set up your lab, this is how you're going to set up your equipment. It's really the same thing, just expanded and in more detail. It's no different.
Very good. Thank you for the question, Vishwa. So our next question, it comes from Anthony Grace, and it's asking around AI. So what impacts on system engineering have you seen from machine learning so far?
A lot, a lot across that entire spectrum. So let's think about AI. Let's first talk about large language models, which has really blown this all up lately. How about you prompt a large language model with the information about a system you want to derive requirements for, and you have the AI help you develop the requirements or help you develop different approaches or feasible solutions, right? Or have the AI look at your data. And I'm talking AI, we're using it, I'm using it interchangeably, right? But the capability of artificial intelligence to help in almost every one of those steps is very significant. Um, uh, the other thing is that one thing that machine learning and AI is good with is taking maybe a set of data and looking for patterns. I mean, that's really what our brains do, and it's what a lot of AI does. And that could be very helpful when we're coming up with different solution possibilities, but also, obviously I was covering this fast. I waved my hand and said, we're going to design something and then we're going to test it. And just testing and evaluation could be a whole 10-week course in and of itself. What machine learning can help us do is look for patterns in data, look for things that we aren't even looking for in context and out of context to say, for example, my machine learning algorithm detected that we have some kind of direct relationship with the vibration of a rotating machine and its temperature. That's something we weren't looking for. And that's where those AI tools can come in, as well as in documentation of everything and finding requirements and doing all kinds of things. So big time. Yeah.
Awesome. Okay, so switching gears to human systems engineering, are there distinctions between that and systems engineering? And then how do interdisciplinary approaches integrating systems engineering with human systems enhance the design and implementation of more effective user-centered systems?
Yeah, so there's no difference that this applies to human-centered systems, user interfaces, all that kind of good stuff. If that's what the question was talking about, you hit something on something very important though. I think it's in the definition in my slides. One of the big pillars, foundations of systems engineering is to look at things as a system and to get back out of our silos. So we're mechanical engineers and electrical engineers and computer engineers, right? So you mentioned human systems engineering or human system interfaces, right? We can't forget about the context of these systems interfacing with humans. And I don't just mean with screens, but I mean, we deal with that in the Navy because we live in and amongst the machines and we have to work in a very confined place. So a pillar of systems engineering is that it's, the word they like to use is transdisciplinary, not just interdisciplinary, but transdisciplinary. And some of that semantics. But what it means is that you would never, even, and again, but even before you were an engineer and you were in high school or you were in middle school, you think about different aspects. You're not just in your one little silo. So what I mean is you wouldn't think about an energy system like a battery without thinking about, well, is this going to get hot? And sometimes when if you've been an electrical engineer for 4 years or for 8 years, and all I'm worried about is power and energy, so it's someone else's problem. Sometimes companies encourage this, which is a problem. It's my job does not involve heat and heat transfer. That's not my job. My job is, how much power am I getting out? And systems supports multidisciplinary work, including human systems engineering, which includes human system interfaces, screens, and uh, uh, you know uh, haptic feedback and all that good stuff, but also the actual physical interplay with humans working with machines. Their size, their shape, their heat, their danger, safety systems. That's another thing that AI and machine language could look for. You've designed something that will tire people out, that will lead to a lot of fatigue, that might injure someone, and you just haven't thought about that. So that's a very big tie-in with the systems process. Yeah, I
Awesome.
hope I answered that question.
I'm sure you did. Okay, so when there is a project manager and a systems engineer working on the same project, how are you able to distinguish the two from each other? Or is that intersect?
So it's really fun. It's a great question. The first thing is because one will be called the project manager and one will be called the systems engineer. Although systems engineers are not always called systems engineers, they're just the engineers. But it sounds silly, but title and you could tell by what they're doing. So a project manager is really looking at the time, looking at the budget weekly, and managing all those things, whereas a systems engineer, even if there's a chief systems engineer, is more concerned about the interplay between the steps and the technical progress. So that slide I showed, that shows the technical flow versus the project flow. It's really, if they're not named that, you'll see by the difference in what they're doing as to which one is which. Yeah. By the way, in many companies and in many functions, they aren't two separate functions. The chief, the project manager is also the chief systems engineer, and they're worrying about both. They're not necessarily separate.
So when you're working on these projects, are there any preferred systems? So I know like Gantt charts are very popular amongst project management. Is there anything that your teams tend to gravitate toward that would be useful for these engineers?
A lot of times it's the tools your company has chosen. If you're not out there being an engineer in business for yourself, it's the programs that your company has chosen. So a lot of people use Microsoft Project because that's what comes in the Microsoft suite they buy. But there are scores of other project management software. I will tell you that when you think about those steps of systems, there are big software. One of them is called IBM Doors, and there's other ones. There's software just for requirements. There's software just for design. There's software for functional analysis and test and evaluation software, some of which is bought, and some companies make up their own. So, yeah, there's no one answer to that. And a lot of it, if you work for a bigger company, you're going to arrive and use whatever tools they have. And you may like it, or you may say, the tool I had in college that we had an academic license for was a lot better than this. So, and that sometimes happens.
Okay, so I'm curious on this one too. So you made a brief mentioning about Boeing and how they got away from using proper procedures and managements. Do you have any examples of companies that you view as doing it the right way?
Well, so before we trash Boeing, for which we have a personal and what Boeing, if anyone wants to see, now that you've seen this presentation, watch a movie on Netflix called Downfall, and it surrounds the whole story of what happened with the 737 MAX. It'll show you how a large, very complex company making a complex product can make a few bad decisions. And believe me, nobody wants that to happen. This is not malfeasance in this case, but how it can get away from you. And that movie highlights it really. And if you watch that movie thinking about the steps I told you, you'll be like, oh, that's what they did wrong. That's what they did wrong. But so I would venture, with a lot of other things, Boeing has done it right. But when you look right now at when you look at, even despite some challenges, how quickly they came on the scene. When you look at Tesla, Apple, I'm trying to think of other companies right off the top of my head that really do this well, that are examples of very popular, well thought of products that are made well and also profitable. All those top, General Electric, Merck Pharmaceuticals, all these companies. And one way I could also let you know about, if you look online and say, who are the top 20 companies that got patents this year, right? You'll get the phone companies, telecom, some of the auto companies, and all. They do this very well. And as much as you hear about the recalls with regard to cars, what people don't always understand is they are putting out millions of cars that work perfectly fine every year. And those cars are being sold to people in northern Canada and in Death Valley, and they're all expected to work. And our tolerance for them failing is very low. So they also do a very good job too.
Awesome. Okay. Well, for the sake of time, if you had just one piece of career advice, because we do have a lot of undergraduate students, and it seems to be that there's a lot of buzz in the chat about potentially pursuing a master's and even going on to a PhD. Do you think it is worth their while, if they are in industrial engineering or mechanical engineering, is it worth their while to take that next step and pursue a master's in systems engineering?
Absolutely. I think a master's in systems engineering is great. I think a master's in your existing field can be great, or one that's adjacent. So I have mechanical engineering as my undergrad, but then materials engineering. But I was in materials engineering working on fiber optic sensors. I mention this because all of my graduate work was part-time. So it's not a bad idea to get into industry for a little bit, see what it is you like or you're passionate about, and then pursue a graduate education. It's never been easier. I did it back where I had to park in a snowdrift at Drexel, getting towed and getting parking tickets. Now a lot of things are online. You could do online at other universities. And also I encourage you, undergraduate education, at least it was for me. I have a degree in engineering management and materials engineering as master's and a PhD. My bachelor's in engineering was absolutely the hardest degree to get. It was harder than the PhD. That was the hard because of the volume of work. So just so you know, you're going through the worst part of it right now. And when you go as a graduate student part-time, the pace is a little less, and you're doing it as a professional and as an adult part-time. And it's really great to figure out what you want to do. I will also tell you, for any of you interested in computers, a lot of people that do controls and other things and computer stuff all have undergraduate degrees in engineering and then went to graduate school for computer engineering and coding and other things, because they know the physics of the machinery, and now they're writing code. But I really highly also, don't worry about, I have to get a master's or I have to get a PhD. Take a few classes. They have certificates where maybe you only want to take 4 or 5 or 6 classes and just take what you absolutely need. Sometimes you can get a certificate and then say, I'm liking this, and then take a few more classes and get the full master's or the PhD. The key is, career advice, lifelong learning is very important. So it's formal. If it's formal with work, that's fine. If it's not, and you're taking training courses or doing something else, then that's fine too. But as engineers or anybody in STEM, you need to continue your education. I teach as an adjunct, and I do that to learn as much as it is to educate. And that's why I do it.
Absolutely. I don't think certificates are talked about enough. They're really great opportunities.
No, and they're a very growing area. They're a very growing area, and they're perfect if you're like, I don't want to do a whole degree, but I want to take 5 or 6 classes that are only relevant to my area. You can definitely do that. Yeah.
Absolutely. Well, thank you so much, Dr. Mastro, for taking the time today to speak to this body of students. We had a really wonderful turnout for summertime, so thank you for carving that time out today. We
You're very
are
welcome.
going, yeah, thank you. We have recorded this talk. So if you want to review it, we'll be posting it to our YouTube. We'll be sharing it on our social channels. Tristan Wolf, who works with Dr. Mastro on the STEM outreach side, he did drop a few different links that are specific not just to Philadelphia, but also to the Department of Defense for different internships and full-time opportunities. If you want to learn more just about what that means, I threw up a couple of different QR codes here. As I mentioned at the beginning of our call today, we do offer small informational sessions where you do get your resume reviewed, and we have the ability to match you up with job opportunities that you can apply and pursue on your end. So really great. It's a really great chance. It's a wonderful career. It's a great part to be a part of our nation's defense. So feel free to scan either one of those. You'll get a follow-up email as well if you do miss this QR code. But enjoy the rest of your day. Take care, and thank you again.
Thanks, everybody. Have a good day.
Thank you.
Thank you for coming.